solids with constant cross sections. Okay. Let me motivate this with a problem. Let R be defined by y equals x squared and y equals 4. A very familiar region to us. Go ahead and sketch R. And don't forget that your sketch needs to include what?
Representative.
Well, we are going to want one in just a minute, but we're not sure about that yet. But it also needs to include what?
The like points.
The like points. What do we call those points? Which points? The intersection points. That's
Of course.
the intersection points. There's white. I can't draw straight. I promise I only had coffee. And so we have intersection points -2, 4 like this. Okay, and there's myself. My region. Now we're going to specify a solid like this. R is the base of a solid. Whose cross sections perpendicular to the x-axis are squares. Find the volume of this solid. This is the usual way in which a problem is posed to us. We're informed that our region is the base of a solid, meaning it's the bottom floor of a solid. And we're told something about cross-sections perpendicular to some axis. It's going to be perpendicular to either the x-axis or the y-axis. And what we're told here is that the cross-sections perpendicular to the x-axis are squares. And what that means is that when I take a mathematical knife and I slice perpendicular to the x-axis, so here is my representative rectangle, then what I get when I cut my solid is a square in cross-section. Now visualizing this is actually kind of a challenge. I find it difficult to visualize in 3 dimensions what this solid looks like. I try, because it's kind of fun, to try to picture it. But honestly, you don't need to visualize it very well in order to find the volume of the solid, and that's good news. So 3D is challenging for you. Fear not, visualizing is not necessary here in order to do this well. What we're going to do to find the volume of this solid is we're going to appeal to the idea of adding up pieces. So I'm going to imagine that this representative rectangle represents all of the cross sections that we take perpendicular to the x-axis. And I'm going to take my representative slice and I'm now going to pull it out of the solid, which is 3-dimensional. The region that I have here is the base of this solid. And when I cut like this, and I look at the cross-section, I get a square. Just like that. So that this is now my cross-section that I'm looking at. Because this is 3-dimensional, you're not going to see a relationship between this and this visually. This is the x and y. When I pull this out, this is along the x-axis, and this is along the z-axis right here. Coming out of the board at you. Does that make sense?
Yes.
Is everybody good so far with the visualizing? Wouldn't it be sloped? Yeah, that's a great point. If I actually try to visualize this, then because my cross sections are squares, then the biggest square is going to have a side of 4, and the smallest square is going to have a side of 0, so that when I look at this guy from different perspectives, for example, if I look at it along the YZ, then my solid is going to actually look something like this, because my squares get bigger as I go. Now the squares are cut now like so. If I try to look at it in profile, oh, I'm going to do a bad job with this. You know me in art. It's going to be bad already. So if this is Z, and if this is Y, and if this is X, which is sort of the standard way of doing this, then the cross sections perpendicular to the x-axis are squares, and I should be able to see something squarish looking out at me. Oh gosh. Yep. Well, exactly. So what I get is some kind of a solid that looks sort of like this, right?
Okay.
And every time you cut into it, along the x-axis, perpendicular to the x-axis, you get squares. But if you look at it along the y-axis, then it's going to be rounded like that, because the radii of my squares is going down. The side of my square is going down. Visualizing this is a real challenge. I actually have software now that will help me do some of these. So hopefully, and you guys probably won't get to see it because it's going to take me a couple of weeks to put it together. But yeah.
So, isn't like solid revolution around the y?
It's not. That's right. It's not a solid of revolution at all. My cross sections are not circles, but instead they're squares. Okay? Well, let's come back to the task of finding volume, because the problem, after all, did not ask us to visualize it. Isn't that a relief? Okay, so how are we going to do this? Well, I'm going to add one more small thing to my diagram right here, and that small thing that I'm going to add to my diagram, I said this is x, but actually this is the y distance, isn't it? Yep, there it is. Because in this direction, my little square has a width of dx. It's not actually a square, it's actually a little tiny box. And I can find the volume of that one box, because we know that the volume of any shape with a constant area is going to be area times width, right? So this is the essence of our volume formula, and that is that the little element of volume for my cross section that I cut out of my solid is going to be area times width, area times dx. And therefore, the volume is going to be the sum of all of the different areas times widths from the first to the last x, from A to B. And that's it. So really, the task for us is simply to find the area as a function of x. And I think we can do that. But to do that, we have to go back to our representative element and ask, how big is it? First of all, shape. The area of our shape is the area of a square, which is side squared, right? So all I have to do is to find side as a function of x. And the side here of my cross-section is the representative rectangle that I drew. And I know how to find that length as a function of x. I know that it's going to be this distance, which is top curve minus bottom curve, or 4 minus x squared.
Wait, Mr. Easton.
Uh-huh.
Okay. So if this representative rectangle square is going like that, right? It's like,
It's coming out of the board at you. Yep.
okay, it's coming out of the board, so it's like.
Yep.
So where is y equals 4? What direction is it going? It's going straight, right?
Y equals 4 is going straight in front of you like you see.
So it's the square is like this, coming like this, and then the line is like this.
Let's do this on the floor. So we're going to visualize it like one of those video games at the mall where they shine down. Right? Okay. So the base is drawn on the floor. We have y equals x squared and y equals 4 drawn on the floor. The solid comes up at you, and each cross-section perpendicular to the x-axis is a square. So I have a bunch of squares of different sizes. They're all stacked up together to make one solid. See it? And now when I take one of those and I pull it out and look at it, I see a square in profile here. I've got a width of dx right there, and the height of that is the same as the width because it's a square. Does that help?
Yeah, I was just wondering about the height, you realize.
Yep. Because it is a square, that controls the height. If it were a different shape, we'd have a different height, and so on and so forth. And we'll do that in just a minute. We're going to keep the same region, and we'll do different cross sections to see what changes. It is going to be sloped in this direction, but each cross section, well, it's going to be slightly sloped, right? So when I pull out any actual real cross section here, then I'm going to get something that is not perfectly a box, but has slight slope. Right? What I'm doing really is I am covering my solid with actual boxes as a rerun sum, as an estimate. And then I'm letting the width of those boxes go to 0 so that my error goes to 0. That's really what's happening. I'm estimating with an inside sum and an outside sum. And that slope right there defines an inside box and an outside box. And as dx goes to 0, it moves to a proof. Great question.
I was just gonna ask, so is this like, are we computing
We're computing an estimate and then doing a limit. And that gives us the actual value. Fantastic question. Okay, so now we're ready to go. Because what we have is the area of this fellow as a function of x, and we're going to check that. We're going to check it at the middle where we have our largest, and we're going to check it at the end where we have our smallest. At the end right here, from our picture, we expect a height of 0 because we have a width of 0. And if I actually plug in x equals 2, I get 4 minus 4, which is 0. Area of 0. Check. At x equals 0, I have a width of 4, so I should have a height of 4, so I should have an area of 16. If I plug in x equals 0, I get 4 squared, which is 16. And so my spot check tells me that I have set up the area probably correctly. Okay? And so now we're ready to go. We can say that the volume is equal to the integral from the first x to the last x, from -2 to 2, of area dx. And that's it. Please notice, no pi, because there are no circles involved. Yes?
Is it always a square?
Nope. We're going to do other kinds of cross sections on this same base. We're actually going to use this region R for the whole day. We're just going to do different cross sections.
Can we ever do this with like, I don't know, like with cubes and spheres?
The cross sections are always going to be planar areas. So not three-dimensional shapes, but two-dimensional areas that are now extruded just a little bit by an amount dx. Does that make sense? So we could do it with squares, rectangles, trapezoids, circles. We could do it with ellipses. Anything that equilateral triangles, anything that we can find an area for. Okay. Now, how to evaluate this integral? Well, the usual stuff. I'm going to appeal to symmetry because my function is even. I'm going to go from 0 to 2 and double it. And it looks to me, my first thought is u substitution, but then if u is 4 minus x squared, du is negative 2x dx, and the x is missing and cannot be repaired. So I'm going to go with algebra instead. 16 minus 8x squared plus x to the 4th. That's x to the 4th, not x to the 11th. And this gives me 2 times 32 minus 8 times 8 is 64 thirds plus 32 fifths. I'm not feeling the simplification today. I think we'll leave that. I could. My inner nerd is screaming. How are we doing so far? So, let's do different cross sections and see what changes. First, I'd like to change our axis. Let R be defined by y equals x squared and y equals 4, and R is the base of a solid whose cross sections we knew that cross sections had a G in it. Perpendicular to the y-axis are squares. Find the base of, find the volume of this solid. Okay, so what changes? Here's what's not going to change. My method is not going to change. If you're a steps kind of a person, here it is. We're going to sketch the base. We're going to sketch a representative cross-section. We're going to set up area equals, volume equals integral of area, in this case, times dy. So I'm going to sketch the base here. Poorly done. You ever have days where you're just a little spastic? I'm having that kind of a day. Okay. So I have my sketch. And now I'm going to draw for myself a cut perpendicular to the y-axis, because the problem says so. And when I do, I get a representative element that is now horizontal. And it has a width of dy. And I'm going to pull that cross-section now out of the diagram and examine it just like this. And if I were to label this in terms of the axes that we're talking about, then this width of my cross-section is dy. The height is along the z-axis, and the length of it is along the x-axis. So that this guy is that guy. Let me shade that just so you can see what we're talking about. This spot right there is that spot right there. It's where the cross-section touched the base. Can everybody visualize that? Okay. And so now I can say that my volume of my cross-section is going to be area times thickness, and the thickness is dy. So I need to come back and find out what that area is. The area of my shape is side squared. So I have to find out what the side is, the length of the side, in terms of y. Well, if y is equal to x squared, then x is equal to the square root of y on this side of the curve, and x is equal to negative square root of y on that side of the curve. Everybody with me so far? so that the length of this fellow from root y to negative root y is 2 roots y. So I can label this as 2 root y because of the representative element. And because the shape is a square, I can label this guy as 2 roots y as well. And therefore, the area is going to be 2 roots y squared, or 4y. And the volume is going to be the integral from the first y up to the last y, from 0 to 4, of area times thickness, just like so. And that's an easy integration. That's going to give me 2y squared from 0 to 4, giving me a total volume of 32. Everybody in your notes do a quick compare and contrast to the 2 problems that we did so far. And tell me if you have any questions. Yes, sir.
Why is that 2 root y?
Ah, because it is the distance from here to here. And so for any y, since y is x squared, x is root y. And the distance from here to here is that x coordinate minus that x coordinate, which is root y minus negative root y.
How about z?
What's that? How about z? The z comes from the cross section. And because my shape is a square,
Square and here.
yeah, that's right. Okay. Good? Good questions. Excellent. Now let's go changing up our cross sections a little bit. Let R be defined by y equals x squared and y equals 4. Fine. Thank you. Miley Chu, after class, Mrs. Bell. Signed, me. R is the base of a solid whose cross sections perpendicular to the x-axis are rectangles of height 3. Find the volume of this solid. Okay. Notice that we have the same region, but now instead of having cross sections that are squares, we now have cross sections that are of a constant height. Basically, what we did was just take our whole region and just extrude it by 3. And so what we want is the volume now. All right? So how is this going to go? If I were being clever and in a hurry, how might I find the volume of this solid? Because it has the constant height all the way throughout. Multiply the area by 3. So we suspect that when we work this problem in the method that we've been using, that we'll end up with 3 times the area of it. And we'll see that that's in fact the case. So we again sketch our region one more time. And we are going to take a representative cut perpendicular to the x-axis, because the problem says so. We're going to pull that cut out of our solid, and we're going to sketch it. The width here is dx. The length right here, I should do it in blue because I've done the others in blue, is the length of my representative cross-section right there. And I can go ahead and label that as curve minus curve, because I know already that its length is going to be that length, which is 4 minus x squared. And the height is dictated by the shape. The height of the cross-section is dictated by the fact that we have a shape that is a rectangle with a height of 3. Done. If you compare and contrast this to the previous problem where we had squares, you can see the difference. This is the first difference right there. The shape determines the height of the cross-section. And then the second one is that the shape determines the area. Because the area is length times width, therefore the area of my cross-section is going to be 3 times 4 minus x squared. Again, I'll do a spot check. When x is equal to 2, I should get an area of 0, because I have basically a line coming out of the board here. And my formula tells me area of 0. Check. When x is equal to 0, my area should be 4 times 3 is 12. If I actually plug in x equals 0, I get 3 times 4 is 12, and I have the right area again. So my spot check is successful. Finally, my differential element of volume is area times dx, and therefore the volume itself is going to be the integral from the first x to the last x of area dx, or the integral from -2 to 2 of 3 times quantity 4 minus x squared dx. Now let's pause to appreciate Tommy's wisdom, because according to my constant multiple rule, that constant 3 comes to the outside. And look at what this integral represents. That integral is the integral from -2 to 2 of top curve minus bottom curve. What is that? That's the area of my region, multiplied by the constant 3. I'm going to do the usual. I'm going to go from 0 to 2 and double it, because we have an even function. Which gives me 8 minus 8/3 times 6, or 48 minus 16, or 32. Which is accidentally the volume of the solid in the previous one. Today's lesson brought to you by the number 32. Can we still do that on Sesame Street?
There's still a Sesame Street.
There's still a Sesame Street. It's become a...
Is Elmo still on there?
I don't know.
What about Big Bird?
Well,
can't get rid of
see,
Big
there
Bird.
was an Elmo scandal a couple of
Yeah.
years ago.
Well, it wasn't really a scandal. It was like, the guy was a... Wait, what happened? Come on.
Off camera, we'll talk about it.
Hey. YouTube
All right.
viewers.
Okay, so let's see if you guys can handle this one. Let R be defined by y equals x squared and y equals 4, and R is the base of a solid whose cross sections perpendicular to the y-axis are semicircles. Find the volume of this solid. I'd like for you to take 2 minutes to do this problem on your own, and then another 2 minutes to discuss it with a friend sitting next to you. Go.
I don't
No
want
help.
to
I don't jump. You don't want to get back right now. I don't know.
There's 3 or 4 people on the high school cell phone.
Oh, shots.
And it's not particularly individuals, it's just the numbers.
No, there's 28 there. Who has the biggest classroom?
Biggest classroom?
Yeah. Or like not in the lab.
Georgia. Or 201.
Either the Strasses.
It doesn't feel big because all those computers along the wall, they can take all the tables out. It's pretty big.
Looking on what?
Yeah. Lydia asked a good question. Where are we getting the semicircles? We are getting semicircles coming out of the page, right? Because the cross sections are coming out of the page. Now, you skipped to do it on your own time.
Yeah,
You should have made as much forward progress as you can. Then you'll know what questions to ask. Doing of it creates questions. Answers the questions. Okay. So what do we have? Gloria, talk to me. Tell me how this goes. As far as we can get. Okay, you're jumping into the middle. I want you to start at the very beginning. Right. We need a sketch. So I sketch here. Did your sketch include the intersection points? Good. If you did not have a sketch, give yourself E squared lashes with wet noodle. Now, in addition to the sketch, I need a couple of more things here. What else do I need visually? I need the representative cross section. And that should be horizontal. Y. Section perpendicular to the y-axis. And now I need one more thing. Sketch. In addition to the base, I need what else sketched? Yeah, I need the cross-section sketched. So in working these problems, I'm going to always have the cross-section and the base sketched out. Just like that. And for reference here, I'm going to color these so that it's clear that those are the same. Okay. Now, where do I need to go from here? Catherine? I sure do. I'm going to need to find that radius, and radius is not diameter. What is that radius? Yes, exactly. It's going to be the distance, it's going to be half the distance across, and therefore we have radius is equal to the square root of y. Very good. Yeah, that's exactly right. That's very good. And give her a hand, because she successfully negotiated a couple of traps. The first is radius is not diameter. It's not the distance across, but half of that. And second of all, the area of a semicircle is semi that of the area of a circle. It's half the matters. Very good. Okay, so now we're ready for volume. Delilah. That's okay. She's done a lot of the heavy lifting for you, so I think you can probably carry it home. So think in terms of adding up. What are we going to add up? You don't have to know for certain. It's okay if you don't know for certain. But I do want you to talk out loud a little bit and process what we've had so far.
I wonder what I know from you.
So,
I'm learning with the integral and from the area instead of problem numbers.
great. Great. That's okay. Let's start with that. That's great. And we're going to be integrating area in terms of which variable, x or y?
Why?
In terms of y. And the reason for that is that our width of our cross section is dy. Just like that. And so that indicates what we're doing. That's good. And that's now the key as to what numbers we're going to be integrating from and to. Because we are integrating in terms of y, we're going to think of our limits in terms of y. That's it. You got it. Good. And now it's just a matter of substituting. Area is, according to Catherine's work,
Or
I think you said pi y over 2. Yep. And we're ready for an evaluation. Charlie, go.
You can take out I over 2.
Good,
And then we'll integrate from 0 to 4 of y u was.
which gives us,
Y squared over 0.
Yep.
0 to 4, which equals 4 pi.
good. Good job, everybody. Okay. Okay. The one that always throws people for a loop is equilateral triangles. So here we go. Let's let R be defined in the same way as before. And now R is the base of a solid whose cross sections perpendicular to the x-axis are equilateral triangles. Find the volume of this solid. And at this point, we're pretty familiar with what we need. We need a base. And we need a cross section. Here's my representative cut. It's going to come out here like so with a width of dx. And now we're going to have equilateral triangles built on top of that. It looks sort of like a pyramid. It's not a pyramid. To make it obvious that it's not a pyramid. There. That's better. Okay. And so now we need to find the volume of this. Again, I am going to mark the dimension here. This distance is top curve minus bottom curve, so I'm going to go ahead and mark my dimension right there. This guy is the same as that. And the area of an equilateral triangle, what is the area of an equilateral triangle? You have 1/2 base times height, and what's the angle right there in my equilateral triangle? 60 degrees, so that area is going to be side times the sine of 60, which is √3 over 2. So the area of an equilateral triangle is √3 s squared over 4 when you multiply together. And therefore, we can do this pretty quickly. The area is going to be the integral of √3 over 4 times 4 minus x squared dx. Problems tonight will ask you to do the same kind of thing, but with different bases.